Okay, so let's get started with the afternoon lecture. As I promised, we're going to get a bit detailed in this lecture, and it will be a detailed description of what you have to face what you'll be facing if you want to do kind of simulations that involve some sort of energy or matter, and then we're going to try to describe which ones may bring more or less complications from the both analytical and numerical front. So piggybacking on Daniel's description, you saw in his description of how to try and understand what the light curves might be associated, say, to the kilonova. And he pointed at some point that the basic key ingredients were the mass of the ejecta, the velocity at which that material is ejected, the chemical composition, etc. So now what we want to do is just how do we go about trying to kind of interface those theoretical models, which are required for more than one reason. So one is we want at the end of the day to have a first principle understanding of what's going on in the source. Those first principle models, which are very natural from the point of view of the discussion, need some input. That input is required to just now get precise numbers, translate them kind of qualitative notions into quantitative measures which tie to the possible observations. And then once you have that, that will allow you to distill which systems or which conditions are good for some particular features in the light curves that you may see, and which are not. And so then that's where you can begin throwing out some possible models and then giving more impetus to some others. So we're going to have to try to take a step back, discuss again numerics, but now in detail. So for all of you that may not be too comfortable with numerical methods, I will kind of reiterate what I said before. Everyone that I see from here onwards is under 30, I think, and as a result, I'm going to use that what I said, that if you're under 30, there is no excuse. You're going to have to learn a little bit of, if it's not precisely doing these calculations yourself, at least to know enough to challenge what type of answers you're getting from some colleagues that may be doing the simulations. So again, to try to kind of make more explicit this whole kind of way or this philosophy that people had. So in kind of previous era, people will tell you, well, numerical activity, which is, as you heard from Sasha Husa, is this kind of sub-branch of relativity that tries to gain headways and insight on the full nonlinear phenomena of the theory by means of numerical simulations. It used to be that you would encounter, and even to this day, you would encounter people that are sufficiently old that will tell you, if you think hard enough, you don't need a computer. I would challenge that statement with the following. So this is actually something that Matt Chopwick would like to say. So with the right resources, you can simulate situations you can't even begin to think through, so you couldn't complete the first step, and thereby provide you with completely new and unexpected things to think about. And he's one of the champions of the field. His kind of painstaking analysis of something you would say is a very simple situation, the collapse of scalar field in spherical symmetry, reveal what and how rich the dynamics is at the borderline between collapsing to a black hole or dispersing away to infinity. Not only that, that was something you would expect. If you put enough energy in a small region, you say, well, it's natural to form a black hole. If you don't put enough energy in that small region, it's natural to expect a dispersion. But what really happens at the verge, that was the most interesting thing. And in particular, he saw the space-time go singular. That singularity is described by a zero-mass solution. And the space-time describes or manifests a self-similar property, all of which could not be foretold even thinking hard enough, I would argue. So again, this was something where the numerical simulations provided some observations, and at the end of the day, the challenge is to turn those observations into real knowledge that you can actually translate back into first principles argument. To some degree, some has been done, but there is a lot, like the example I mentioned today of a black hole that just moved through a plasma generating a jet. There would be good arguments that you would have in the thinking hard enough side to say cannot be a jet, and then the simulations show you that they're not only there, you challenge you to try and provide an understanding. So once you kind of buy that argument, if you do, then you're going to have to kind of tackle this set of questions. Well, you want to solve Einstein's equations, because after all, we're trying to understand strongly gravitating systems and how they are able to spew tremendous amount of energy, either in gravitational waves or anything else. So you know the left-hand side of this equation is a nonlinear partial differential equation. Describe a little bit some particular peculiarities that this system has in contrast with those of hydrodynamics. In the right-hand side, you have the source, which somehow you're going to have to account for. You're going to have to provide what is your assumption of the matter content in your spacetime. And then you're going to have to evolve once you provided some initial boundary data with some set of evolution equations. You're going to deal with some issues like coordinate singularities might arise, and you're going to have to somehow react to them. And in the case of non-vacuum scenarios, then you might have, for instance, if you're dealing with fluids, you're going to have to deal with perhaps shocks, the microphysics that is involved, and in itself, it's initial and boundary data. The other thing, I try to open this thing to see what has gone on with the battery. The other thing is that the decisions you make will have some dependence on what your computational resources are. For instance, if you're trying to solve ab initio, the core collapse supernova problem, I would say don't bother, because you cannot do it in full generality. You have a system that has strong gravitational fields, have strong fluid dynamics, but the microphysics involves an intimate knowledge of what's going on with neutrinos, and neutrinos are described by a 6-dimensional representation plus time. So there is no way today, and the 6 dimensions are where each neutrino is in space, and what its momenta is in space. To solve that problem in full, it's impossible nowadays because the computational resources are limited. So you're going to have to take some shortcuts, and people do take some shortcuts, and the result at the end of the day is that some things are understood more or less in a robust manner, but there are many other points of contentions which are traced back to the fact that you actually are not solving the problem in full generality, and different shortcuts influence the solution in a significant manner. So your computational resources coupled to the algorithm issues for each particular model that you might have to deal with, then will come and be part of the relevant question. In some sense, you're going to have too many options, and what we're going to try to is just distill what are the key ingredients that you need to worry about. Either you may address with some of the things we'll discuss today, or at least you know what the issues are, so that when you go and try to describe a particular, employ a particular algorithm, you're going to be able to address the peculiarities that you'll have to face. So just as a last point, I want to say, forget about that usual kind of this fake description that, okay, you could do analytics versus brute force numerics, because there is a lot of brute force analytics and elegant numerics as well. So it just depends on the eye of the beholder and how, at the end of the day, how successful you are at dealing with the particular physical question you have in your hands. Once you're taking that decision of go computational, and you have heard already several lectures of those, in particular Sasha went into quite a bit of good detail, there's no need whatsoever to lower your standards. The computational simulation is not an excuse to be sloppy. If anything, it's the opposite. You need to be as careful as you have to be at the analytical level, because many of the issues you're going to encounter will be resolved once and only if you understand what the analytical problems are. And then once you understand them, what particular method you're going to use will define the problem you're solving. And then we're going to try and discuss some of those. And I'm going to put this definition. There is this beautiful book by J.P. Boyd on spectral methods, and has lots of cute definitions. And he has this definition 16, the definition of an idiot. And I tell you, anyone that publishes a calculation without checking the calculation against an identical computation with a smaller n, i.e. Anyone that publishes a calculation without a convergence demonstration is an idiot. And so he has a disclaimer there. I'll also use it. And the other thing he says in his book, which is also very important, a computation is a temptation that should be resisted as long as possible. So you have to make sure you know that that's your last resource. In some sense, it is the right tool for the problem you're trying to deal with. And I always will say at the end of the day, the best code, the best numerical implementation you write, carries the seeds of its own destruction, i.e. the most successful code will provide the richest solution. You're going to understand enough of the problem that at the end of the day, you're not going to need the code anymore. That should be the underlying philosophy, in my mind, of any numerical simulation. And this is the reason why, while you might hear lots of people naming codes, they say, oh, you hear about this code with this name, this code with our name. If you ask what my code's names are, I don't have codes. I usually joke, I come from Argentina. You never name the animal you're going to eat. So you're going to kill an animal, so you don't name the animal. And I want to kill my code. At the end of the day, I don't want to use it anymore because I learned enough to keep going. OK, so I'm going to just start this way. Let's go back to some problems you already discussed with Sasha Husa. And I'm going to kind of start with it as a launching platform of what is it that differs once you start studying things like hydrodynamics, like matter. So let's take, for simplicity, that second-order wave equation. This thing works whenever it wants. Let me try this other one. Remember, you were going to stop me, so ask questions. So let's take that equation as a second-order wave equation. So one thing we could do is just try and insist that we're going to write things in terms of first order. And I'm doing this just to motivate some of the things we're going to see when we look at hydrodynamics. So let's introduce this variable, which is just a time derivative of the scalar field. This variable, which is a spatial derivative of the scalar field. And we can rewrite this system in terms of these equations, or these relations, in this way. So just a time derivative of the field phi is equal to g. The time derivative of the field f is the gradient of g. The time derivative of g is the gradient of f. So we have that system of equations. And for many reasons, it's going to be convenient to write it in matrix form. So we just take all our unknowns. We're going to put them in a vector. And then these equations can be translated into the following. The time derivative of that vector is equal to this matrix times the gradient. And I'm forgetting here another vector which should have 1, 0, 0 multiplied by, so a matrix that has, I'm forgetting a source, which will be 0, 1, 0, 0, 0, 0, 0. So once I have this system of equations, I can write it this way plus that. So the first thing we do when we look at this is to ask, what are the eigenvalues of this matrix? The matrix multiplying the gradient. And then we can draw already quite a bit of information of whether we should take the next step or stop at that stage because something might be going wrong. So the first thing we notice is that if we compute the eigenvalues, they're all real. They are 0, 1, or minus 1. So that's a good sign. It says that at least the system is weakly hyperbolic. If we had any of these eigenvalues be imaginary or have an imaginary part, then this will guarantee that the system, that any problem study cannot be well posed. So this is something where you shouldn't even attempt to go on the computational level, because already at the analytical level there are problems. And perhaps, I think, depending on how we go, the last class, I'm going to show you how nowadays there are many systems that have that property. Those systems come from the desire to test some particular extensions of general relativity, but they have these problems. And then somehow you need to pause and decide how you're going to take the next step, because if you just take it blindly, put it in the computer, things will just blow up in your head. The other great thing, not only it is the case that these eigenvalues are real, there is a complete set of eigenvectors. So now this at least is telling you is you're better than weakly hyperbolic. You are perhaps strongly or symmetric hyperbolic. And this is as good as it can get, especially in a system that is not linear, especially in a system that has lower order terms. You can prove quite general theorems that said if your system doesn't satisfy this property, it most likely is the case that the system will render any problem ill-posed. Again, it's something where if you put on a computer, it's going to fail. No matter what trick you pull, it's going to fail. So are we at the same page here? So piggybacking on what you just said, the conditions 1 and 2 means this is a strong platform for any numerical implementation. You will know that at least locally a solution exists. Where the solution will exist globally, that's a completely different problem. Just as an example, the Navier-Stokes set of equations is awaiting someone to prove global existence or general failure, and that person will get $1 million. So that's, and it's not, we're not talking about relativistic hydrodynamics, we're just talking about Navier-Stokes. So it's Newtonian hydrodynamics, we still don't have that answer. The answer exists in 2 + 1 dimensions, but no one has it in 3 + 1. So that's a good thing, that's a good project. Someone wants to pick up that project, all the power to you, and I hope to be celebrating when you do it. But I'm a lot more limited, so I cannot go there, and the most I'm going to be content with is to at least know that locally I can ask questions to my system. The other thing we get is that the system is not overly sensitive on the initial data that we choose. So any initial data that we may choose, and with small departures around that initial data will give me roughly qualitatively similar solutions. And we can make this much more rigorous. We can express this in terms of Sobolev norms of differences, etc. I'm not going to go there. I'm just telling you some of the right things that work for us if we satisfy those properties. Also, if the eigenvalues are bounded, those lambdas that we chose there are bounded by some value. This is a very good message for the numerical implementation. The time step we can choose, and this is something that Sasha described, this thing called the CFL condition, Courant-Friedrich level condition. Do you guys remember that? Yes, no, I don't know. There are crickets. So there was this condition that, let's say if you have this equation, delta t proved quite generically that will have to be related to delta x with some proportionality factor, and this proportionality factor is related to 1 over the largest lambda that you have in your system. So if now you imagine the lambda is huge, then your time step will be very, very tiny. And that will have an implication how long can you solve the system for? How long are you willing to wait to get the solution? For the right type of problems, and this we'll discuss later, we might get away with doing something else, but we need to understand what is the price to pay. But if we did our study and the eigenvalues are not only real, but also bounded, that's good, because we know that at worst we're going to have a time step that is not too small. And depending on the solution itself, this point that it's not very dependent on initial data, that tells us at least locally, if we choose a very smooth enough initial data, we can use that in the type of discretization strategies we're going to use. At least we're going to say that in some neighborhood of the initial data, we don't expect the system to have very, very high frequencies. So why is that we keep insisting on the system? Now let's just make it a little bit more general. Let's imagine that we have a vector of unknowns. I'm just labeling here U1 all the way to UN. The time derivative of that, let's say, is equal to some matrix times the gradient of it. Notice that I forget again some extra piece, which would be undifferentiated parts in the right-hand side, just like this one. The reason for that is that if all the eigenvalues are real, and I have a complete set of eigenvectors, this piece that I'm forgetting doesn't really matter in a significant way. It matters in the solution I'm looking for, but it doesn't matter with respect to given some initial state, whatever that is, and I ask how will perturbations propagate. They only care about this first part, and this is therefore called the principal part of the system. If we didn't satisfy this property, then we would have to analyze the full system. So luckily for us, all the equations we're dealing with that do satisfy this property by and large. And the other thing that this property here tells us is that even though we might have this equation with a very complicated matrix in there, implicitly, we just have a whole bunch of advection equations, a whole bunch of equations that look like that. So the proof is trivial. That goes back to your linear algebra first course. So suppose you have that equation. This is the one we just wrote. And then we just said that there is a complete set of eigenvectors. Therefore, if that's the case, there exists a transformation that will take the matrix into the diagonal one. And so we can now use this relation and rewrite our equation. So take this m and put an identity in front of it to the left. So I'm going to construct it with t to the minus 1. Put an identity in between m and the gradient of u in between. So I'm going to construct it with t to the minus 1. Why did I do that? Because now this piece here is the diagonal that we had over there. So I can multiply now on the left by t to the minus 1. And so now I can have a t to the minus 1 here with t that will give me identity, and I can throw that away. And I have this t to the minus 1 u comma x here. So now, remember, we multiplied to the left by t to the minus 1. So this thing in here, I can rewrite it by grouping. So I can take t to the minus 1 times u, the whole thing gradient with respect to t. And of course, I have to take whatever I added for that, which is t to the minus 1 comma t times u. And the same thing I do here. I can write as t to the minus u comma x minus t to the minus 1 comma x u. But notice what I have in here. So now I'm having here t to the minus 1 u comma t, and here I have t to the minus 1 t to the minus 1 u comma x. So let's call that v, t to the minus 1 u. So this is v comma t equal d v comma x plus pieces that have no differentiation on u. And I already said, excuse me, I already said that if this diagonal has all eigenvalues that are real, we really don't need to worry about the rest. So once we see what we have in here, we just have a whole bunch of advection equations. So it's just v1 lambda 1 v comma x, v2 lambda 2 v 2 comma x, etc. So, and this is the reason why we keep going back to that very too simple looking an equation, is because it underpins pretty much everything we say on hyperbolic problems. There's a beautiful book by Gustav von Kreis and Olliger. It's about this thick. It's by applied mathematicians, core applied mathematicians, and it's just pretty much the only equation they solve there. This one. And they prove very generic theorems. So now let's use that to our advantage. Now that we have understood that at the core, or the heart of hyperbolic systems, is we just have a whole bunch of these. Let's keep, for the moment, thinking about this type of equation, just the advection equations. So the moment we see these, we know that at least locally we can write a general solution, and the general solution will be some arbitrary function, which is determined by the initial data itself, times lambda t plus x. So if we plug this general expression in here, I'm going to have f times lambda, and f, and this has the right-hand side, I'm going to have lambda times f, right? So I take it the derivative of the gradients. So that's its general solution to that problem. But we know a lot more now, because the sign of, the sign of this lambda tells you which direction propagations move. If this lambda is positive or negative, so if lambda is positive, we're going to have a pulse that moves from right to left. And if lambda is negative, we're going to have a pulse that moves from left to right. So is that clear why? So we just said that the general solution is going to some arbitrary function f of lambda t plus x. So at time equal to 0, let's say at t equal to 0, we have f of x. But at t equal 1, we have f of 1 plus x. So that means that if I take the x and I displace it by 1, I'm going to have the same shape. So the sign of it tells us if where it goes to left or to the right. Where are we going to use that? Well, we're going to use it in boundary conditions. We're going to use it to understand whether an object is acting like a black hole. If everything is falling into some small region, we're going to say, oh, we don't need boundary conditions there, everything is falling in. That's one of the tests that we have to understand whether we have a black hole or not, or whether we have a wormhole, which is the analog for fluids. We also know that if lambda is 0, times we have the repeated function, so that we have something that doesn't propagate, and so on. But now is where we'll begin to kind of differ a little bit from what you heard in Sasha's talks. So Sasha was mainly concentrated on what you need to do at the numerical level for studying, say, something like the binary black hole or electrodynamics. But now we want to transfer or move to the problem of hydrodynamics. So what happens if instead of this, if in the case of lambda, instead of being a constant, it's a function that depends on the unknown itself? And sorry, I have now changed the notation to q comma t equal q comma x. So my lambda, I have now just defined to be q, let's say. And the reason I changed the label to q is that if you open general books in hydrodynamics, they use q for whatever reason. So now, what we have is a very obviously nonlinear equation, while before, if in this case, if lambda was a constant, we had a purely linear equation. The solution, two solutions added up will be a solution. But the moment I have that, it's no longer linear. And so here's where we have to take the first practical shortcut. And this is generic. In general, nonlinear equations, the solutions are not known. And remember, this is what I told you before. This is like going back to that statement of Ulam. By and large, people have been studying linear problem or problem that have been linearized because that's all we can do. So we're going to do that again. Of course, our goal at the end of the day is to be able to have a code that allows us to tell what's going on in the full nonlinear problem. But let's just imagine you take this one and linearize with respect to a given background solution. Just call that solution Q0. And then ask the question, how will perturbations propagate off it? So I write Q is equal to Q0 plus some delta Q, and I'm asking, what's the equation of motion that delta Q obeys? So I plug that in here, keep only linear order terms, and I have the following. Delta Q comma T equal Q0 times delta Q comma X, and you should be telling me I forgot a term. What term did I forget? Someone should answer, or we stop here. Say again? Right, so we have a term missing here, which will be delta Q times Q0 comma T. Right, so what I did is we took this equation, and then I replace Q by Q0 plus delta Q. And we're saying Q0 is a general solution, so it could depend on both time and space. So when I plug in here, at the linear order, well, I'm going to have Q0 comma T. Let me write everything. Right, so now at the linear order, things that don't have any delta, I have Q0 comma T equal Q0 comma T. But we started saying that Q0 was a solution, so that has to be satisfied. I can throw it away. At the nonlinear order, sorry, at the linear order, I have delta q comma t. Then I'm going to have q0 times delta q comma t. So this times that. And then I have delta q plus q0 comma t. Sorry, comma x. This should be x. Yeah, thank you. But we started saying this is a 1D equation where that q is real. Therefore, by virtue of the properties we said before, we don't need to worry about the undifferentiated part. So this is delta q appears undifferentiated. So for the propagation of perturbations, the only thing we care is about this. Of course, the true solution will depend on the term that is delta q undifferentiated, but we're asking perturbations. So now we have the following issue. We have a velocity here that is space dependent. So imagine that our q0 had this shape. So it's negative here, it goes to 0 there, and it's positive on the right-hand side. So now all these have positive values, and we know positive values move to the right, the left. So this has all these things moving to the left. This one that has negative values of q0 have all these pieces of the solution moving to the right. And this one is not moving at all. So what we have is something that will get steeper and steeper and steeper. Furthermore, this value here is larger than the value here, so this one will catch up to this one and will generate what we know as a shock. So there are two different phenomena that we can have, shocks and rarefaction waves, and we'll discuss both of them. The other thing we need to worry is that at some point characteristics will cross. If characteristics did not cross, like in this case, we had the argument that the only thing we needed to do with the pulse was to move it left, right, to understand how the pulse will behave at a later time. But if different pieces are moving at different speeds, at some point, 2 points in time get evaluated by two different characteristics, and then we have to deal with the lack of uniqueness. So past this point, is the solution governed by what it had over here or what it had over there? These are the questions that we need to address when we talk about hydrodynamics. We didn't have to worry about that in the case of general relativity. The reason is that general relativity in many ways is very special. This is why mathematicians have a special name for those kind of solutions, those kind of equations. They call them linearly degenerate. They are nonlinear in the sense that you cannot add two solutions and pretend and hope that you have a third solution, but they are sufficiently linear that the propagation of perturbations do not really care so much about the state of the system at any given time. So now how do we address that problem? We have a system where we lost a whole bunch of things. We lost smoothness. We initially put something that was smooth, and then it steepened itself. Of course, two common examples, unfortunate, of this kind of phenomena is traffic, right? Someone slams on the brake, and then all the cars, either they pile up on top of each other, that's not a good sign, or at least they just cram in such a small region that the density, the effective density of cars per, 10 meters shoots up. Then, at some point, the leading, that will be an example of a shock. At some point, the cars that stop first begin to propagate out, or just they speed out, and then you generate this vacuum behind them where the density goes much lower, and that's a rarefaction, but we'll look into that explicitly. So how do we deal with a situation where not only are we losing smoothness, but we're also losing uniqueness? So the right approach is to first consider general solutions that are called weak solutions. So you just take the original equation of motion that you had in here, multiply by a general scalar function, let's say in one dimensions, and then use iteration by parts to turn this equation into this one. So the only thing we did here, notice that if we iterate by parts, we have dt of phi q. So that would be this term. And the same in here, So this equation that was originally equal to 0 gets turned into this one. Now derivatives of this generic function phi in time times q plus f. So I now have written the equation of motion in this way. For reasons that will become clear in a second. So I was just saying, the rate change of that variable q times some function of q equals 0, t, comma x. So now we turn trying to solve this equation into trying to solve these other equations for general values of phi that we can consider. These are trial functions. What one can see is that there are many more solutions in here. So there are a whole set of solutions, and there's not, uniqueness gets lost. This is what we were saying about the crossing of characteristics. But you can reinstate and recover uniqueness if you ask for another conditions on top of it, which is the condition of maximizing the entropy change in the solution. So you say, well, the most likely solution that I'll get in a physical system is the one that is preferable because it gives me the highest rate of change of entropy. So we're just using entropy considerations to pick that unique solution. And because of this weak sense in which we're doing the calculation, there is an iteration strategy that is very naturally motivated, which is that of so-called finite volume. So formally we're going to discuss this. In the end, then you can recover in many other ways. But let's take the standard form. So at the core of these methods is recognizing the following. So imagine you have this equation, and now imagine a cell in space. This is telling me that the rate of change of q has to do with the gradient of some function equal to 0. So now I can imagine iterating this in the cell. So I'm going to iterate in dt and dx, the whole thing. But then the neat thing is that once this operator, this integral in the acts on the q comma t, we can iterate it by parts in this piece. And the only thing we have left is the evaluation of the integral of q dx at right, one at this time and the other one at this other time. When we act with this one on this other term, on the end, one acts here, we can again use the integral, the parts, and turn this into something that really. So graphically, what we're doing is saying this appears as though we're computing how the average of the quantity q at this time in this cell changes new value here by virtue of whatever flux entered through the cells. So is that clear? So this is at the core, and the other thing we're going to do, or we're going to exploit in the methods, is to consider each cell in some sense independent. So the solution might just go completely discontinuous in between cells, and we're going to use that to generate a particular method that picks the right solution, addresses the lack of smoothness, and does so in a way that we can guarantee that the solution we're getting is a correct one. So at the bottom line, what are the things we're going to be relying on is that first, we're writing things in a conservative form of the equations. The reason is because we want to make contact with this way of thinking. Some average quantity changing in 2 times because of fluxes through cell interfaces. We might have a source that will alter things a little bit, but okay, we're going to integrate the source in a particular way. This is not a big deal if we have done this correctly. That will also motivate rewriting the equations in a particular way. So instead of writing something of this form, the time derivative of u, sorry, we go from q to u again, so we're going to be going back and forth between u and q. The time derivative of u plus some gradient of some flux is equal to 0. If we are presented with this equation does not have that form, so we're going to prefer, and I'll show you some examples, rewriting this piece in this way. So we're going to write u comma x as the gradient of 1/2 u squared. So there will be two theorems that kind of underpins everything we do. One is one by Lax-Wendroff that basically tells us if a method is in conservative form converges, then it converges to the weak solution of the conservation law. And then a theorem by Hugh-Lefloc is in a method in non-conservative form, i.e. if you're using this one, and convergence in the presence of a shock wave, you can prove that the convergence will be to a wrong solution. So these two theorems tells us, well, go in the convergence form and it will give you the correct weak solution. You're going to impose through the jump conditions the uniqueness. And Lefloc tells us, well, if you try something else, even though you might have a solution that you can, with all the tests as such explain, you can swear to God that is a convergent solution. When you decrease the grid size, Lefloc will tell you, well, that might be the wrong solution. You just picked up one of the many solutions we argue you could have, and that would be a bad thing to do. So let me just walk you through some more details about this, and then show you some explicit examples. So we're thinking of this equation, but we're going to iterate in time and space, as I alluded to here. And so once you do that integral, then what you really have is kind of the average of the value of u in the cell at times t(n+1), so this would be there, equal to the average that it had at the previous time, plus 1 over dx, the flux at the left cell minus the flux at the right cell. And that's the method you're going to do. In more compact form, well, it can be written this way. The average, and this is when the over bar means the average. So the average over that cell, which has center label I, equal to the average of that cell at the previous level at the same center times minus delta t over delta x of the difference between the fluxes. So they say, well, whatever enter one side and left on the other one, or vice versa, will make up the conditions to change the average from this one into that one. And the different numerical schemes will differ on how you compute the fluxes, because that's the only thing that's left. Here we have the average of the function at one level and the average of the function at the other level. So different schemes will differ on how you do this. So let me just give you some examples, so then we'll see them in motion or in action. So let's say you stick to first order schemes. So just first order in time, first order in space. That's going to be your error. And so this is the same equation we had before, ignoring all the issues that we said about shocks, discontinuities, the issue with fluxes or averages. We're just imagine that we picture this. You take the value of the cell at n+1 at the center I, and then average the cell at the left and at the right of the one you're trying to iterate. And then you just do this, where the fluxes here are just simply evaluations of using these values, what these are. So this is just a simple first order in time, first order in space method. The method is stable, so it's not going to blow up in your face. But you can ask what's going on with the solution. So at time 1, so this is in a periodic case, it's showing what the true solution should be in solid line, and the solution you're getting with that scheme with circles. So it's not too bad looking at t equal 1. Okay, you have kind of smeared out a lot of features, but as you go to later times, then you're beginning to lose completely the solution. So this may be stable, but very quickly, the solution will be completely worthless. So let's say, well, maybe the problem we had is that we were not very accurate. Let's try to increase accuracy. Maybe we keep the first order in time, but let's do something better in second order in space. So we introduce a second order approximation to the right-hand side. This a well-known method called Lax-Wendorf. We can look at the details later. And that one does better at keeping the features. So these are t equal 1. So somehow, well, t equal 1 is not too bad. At t equal 5, still you have some structure. But now you begin to see spurious oscillations. So here they're clear, and then this oscillation begin to propagate. And also, at a later time, you might completely lose all confidence in the solution. So these are two methods that are written without trying to kind of negotiate in the right terms the features of the solutions that are arising. So we need something better. We need a clever idea, and Godunov brought it for us, and so we'll describe that as we go along. So this is what I was saying before. So second order accurate schemes with artificial viscosity. You saw this with Sasha Husa. So Sasha described the addition of artificial dissipation, right? I think I saw that in one of the lectures. If your solution is initially kind of doesn't have a lot of high frequency, it's a rather smooth object in your representation, and energy stays mainly at those low frequency modes, the artificial viscosity is great, because it's just simply there to try to address the fact that at very high frequencies, the truncation of your numerical approach is continuously adding some source of high frequency. So you want that to control it. But in the case where we have shocks, where smooth solutions turn into very sharp ones, then you're going to be killing your solution. Remember, in many cases in hydrodynamics, the shock is the physics. The huge discontinuity in density, for instance, is what describes where I'm standing on. There is a huge difference between the density of cement, I hope that's where I'm standing on, and the density of air. If I'm using, and even though it's a stationary problem, if I were to use one of these methods that has high frequency dissipation, at some point the difference between the ground and myself and the room will just get all blurred into a single thing. We don't want that. So we need better methods, and one of these methods, or what the Trojan horse of these methods, is called Godunov methods, where discontinuities are not trying to be erased, smoothed out, or whatever. You're actually going to embrace them. You're going to say, well, I'm going to live with the fact that they are there, and I'm going to just follow it. I'm going to exploit the fact that I know analytically. And this goes again to what I was trying to say at the very beginning. You need to understand as much as possible the analytical features of your problem so that you can do the right job at the numerical level. So these methods exploit the fact, or recognize the fact that discontinuities will arise and will react accordingly. They are based on the solution of Riemann problems, and I'll define what a Riemann problem is in a second. Their second order schemes are even higher ones that can be derived without these problems here, where kind of artificial spurious oscillations are introduced. And the state of the art in relativistic hydrodynamics is this kind of family, is based on this family of methods. So let's define what a Riemann problem is. So we're going to look, as opposed to kind of the artificial viscosity idea, where you say, well, I'm going to rely that the solution lives in the low frequency modes, and I'm just going to control the spurious frequency modes. Here you're just going to go head on. You're going to say, well, I'm going to look at the worst possible case I can imagine, which is a state where the solution across some given interface has a big jump. So let's imagine that the solution, and let's say even this is our initial data, at t equal to 0, I'm going to define the value of u to be ul, whatever value I want, and ur. So, but I'm going to make them discontinuous. And I need to deal with that. So a Riemann problem is this problem where you actually think of two states with a given interface where there is a significant jump, and then you have to deal with it numerically. So let's see what our ingredients are, and what we know and what we can guess from what's going to happen. So we go back to Berger's equations, we argue, at least I hand-waved, why is that we prefer to write it this way. And so this equation we're showing again and again has its own name. It's called the Berger's equation. And so the rate of change of Q, and I go back to Q, sorry, is 1/2 the gradient of Q, actually, this is a typo. It should be Q squared comma X. Now let's assume some basic ground rules. Let's assume that we're going to give data where Q at 0 is greater than 0. So we know that this pulse will move to the right, because I have it written here in the left-hand side. Had we move it to the left, to the right-hand side, we would have a minus sign, right? And that would be a negative eigenvalue. So the pulse moves to the right. And now let's define the first Riemann problem, or a Riemann problem for this equation. So at the initial time, say with an interface at x equal to 0, let's define the value q to be q left, and very effectively at the right side of the interface, I'm going to call it q right. Now let's consider two scenarios. One where ql is greater than qr. So we're picturing this. This ql, this qr, and everything is greater than 0, let's say. We can even choose this equal to 0, but let's say we're picking that. So, and we're only looking at this. I have, again, this advection equation. I have q comma t equal a constant, because that's what I gave as initial data, times qr, so it's going to be moving to the right. But ql satisfies the same, so it's going to be q comma t equals some value times q right. It's going to move to the right. But this one is moving much faster than that one. On the other hand, we can consider the other case where, let me just do it on top of here. Let's imagine that we have this other case. So if we have qr is going to the right, ql is going to the right, but this is going faster than that one. So this one is going away from this one. This one cannot catch up. So in one case, we're going to have this one run onto that one, and we're going to steepen the profile. This one is not catching up to that one, and then we're just going to open up what is called a rarefaction wave. So let me just give you a couple of examples. And so here is a problem where I'm going to, because of this problem being sufficiently simple, one can find the true analytical solution. This is known. We might have some homework on that for you to find it. And we're going to solve it. We're going to use a Riemann problem, which we're going to describe later on, and then just study this case. So this is the first one we described, where QL is greater than QR. So let's just look at this. Oops. So now you see, in red is the analytical solution, and in blue is a numerical one. So it's doing pretty darn well. And for a while, this t equal 1, I just follow it. Notice that it had no problem with that huge discontinuity. So somehow, whatever we wrote was able to cope with that. Remember in the techniques that Sasha told you, how you computed a derivative by finite differences. You took the value of the left minus the value of the right, or the value of the right minus the value of the left divided by delta. Imagine you had a grid point here, another grid point there. When you take that difference, it's going to be huge. So somehow, the numerical method is able to cope with that situation without blowing up on our faces. So now let's look at the other case. The left is moving slower than the right. This is called the Riemann fan, or the rarefaction. Ouch. So the red is a true solution, and the blue, sorry, I went too fast. This is the one I wanted to show. So the red is a true solution, and the blue is the approximate. And we have boundary conditions so that everything that gets to the right just leaves the domain. So again, this row solver is doing a pretty good job compared with the true solution. So now let's compare with two other cases. So here, we're going to have the true solution compared with the upwind non-conservative case. So let me just explain what this is. So first, here is the method applied to this equation. Upwind, how many of you know what upwind means? Raise your hand. No? Okay, perfect. I'm going to tell you what that is. So the method that slants the derivative calculation this way. So you're going to say, let's take the time derivative using these 2 points. Let's say we're considering this point. So this is we're going to take the time derivative in this using these points. But the space derivative, I'm going to use these 2 points. So it's not, let's say this, we have this hard green. It's not the center derivative. I'm not taking these 2, taking these 2. Why do we do that? Well, because we know that had we taken these 2 points, that would have been the first order in time, center in space algorithm, which is known to be unstable. So that's a bad idea. We know by our analytical discussion that the fluid is moving from left to right. Because of that, the true correct slanting is to the left. Had we slanted to the right, that would have been unstable because there are pieces of the solution. Here is analytically going to be determined by the. And if we slant to the right, we're not accounting for it. And we will be violating this Courant-Friedrich-Levy condition, the CFEL condition that Sasha discussed. So we're doing that. And we're using first order in time, slanted in space, which is this upwind. And where you slant on one way, on one side, or the other one is called either upwind or downwind. Not very creative, but that's what we're doing. So here, the solution we'll see is stable again, but very quickly develop a significant difference between one and the other one. So remember that theorem by Lefloc. It told us if we have a convergence scheme and you're not using a conservative form, you're going to converge to a solution that is not going to be the correct one. Because here is just a demonstration of that fact. Again, we can say, oh, so now let's pay attention to poor Lefloc, because after all, he worked hard for that theorem, and write it this way. So we don't do any other change except that that's what we write. So here we have the difference of the derivative of q comma x, q squared comma x. So we take q squared here, minus q squared there, and divide by delta x. So just a straightforward implementation. And now we're doing a pretty good job. You can see a little bit of a difference there, but by and large, we should be very happy with ourselves. But then you say, well, actually, higher accuracy because after all, I just wrote this, I don't know, general relativity code for the gravity part. This happens to be 6th order accurate. Why am I losing so much accuracy in the hydro? Well, you might have to live with that. But let's say you're a very diligent person and you're going to do a higher order scheme. So we're going to use the conservative form of the equation, but now implement the 2nd order approximation to this. And let's see how it goes. And we're doing awesome here, but we keep dealing with that thing. So that thing is just introducing some very, very high frequency noise that we would like to avoid it. So what is it that these high resolution shock coupling methods have? Well, they solve the full problem as a series of Riemann problems between cells. They enforce a total variation diminishing. So they enforce some properties that the variation point to point at one level is larger than new level. So you're trying to minimize those spurious oscillation. They exploit the characteristic structure very explicitly. And I would say there are too many options. There is an awesome book by Randy Levesque, all about hydrodynamics. There is many possible options you can choose. But let me just backtrack a little bit and say, what are all these methods differ with respect to each other? By and large, they differ in the following. So I just told you that we were going to try to solve the full problem as a series of Riemann problems. So that was a bit of a white lie. They don't solve the Riemann problem exactly. They solve a Riemann problem approximately. So they just approximate the Riemann problem in a sufficiently good way so as to kind of recover all the nice properties of solving the full Riemann problem, but not having to deal with all the complications that will arise in trying to deal with something that has a very nonlinear structure. So what you do there is just, in some of these, or in many of these approximants, is you approximate the flux in a way that actually renders this problem into locally a linear problem. So let me, I think, given what I'm gonna choose next, I'm gonna just describe explicitly one of these solvers. And this is a solver that was used in the first example of these shock problems. Remember when we discussed the shock problems under rarefaction fans? This is the technique we were using. So we start with, the rows. So we started with this equation. So that's our equation. It could be Berger's equation. It could be the full hydrodynamic equations. We're going to discuss them tomorrow. Now linearize, locally linearize, and turn this problem into the following. So I just rewrite this as a derivative of f with respect to q times the derivative of q with respect to x. Now everything will be in here to understand what is the characteristics of this matrix. So the row solver will basically say, well, now we're going to evaluate the fluxes. I'm going to let me write this first, and then I'll tell you what the ingredients are. me turn on the lights. So let me just discuss a few things that are here. So this is the flux. So we're imagining we have a cell at some given time on the R1s, and we're trying to obtain how the average of the function, say Q, changes from here to there. So this would be flux that we need to compute. And if this is the cell I, this interface I plus a half, I minus 1/2. So now what I'm doing is I'm computing flux or evaluating that flux by adding several pieces. Let's discuss what this one is. So this is the flux that we evaluate. Note that I'm writing P. I'll tell you in a second what that P is, but imagine for the time being that is Q. At I plus a half, so I see cases, except that I see R as a supraindex here, and I see an L there. What is that? That says take from the cell, and depending on what you're doing, from the left of that cell, a way to approximate the values of your functions here at these cells, and call that left, because you're coming from the left at that interface. Do the same thing on the right side and get an approximation from the right. And then you're going to add another piece, which is the sum over all the eigenvalues of your system. In our case, if we have the Burger's equations, we have only one, so the eigenvalue will just be Q. But if you have, and we're going to describe this tomorrow, multiply the eigenvalues, and this is why we were concerned with the eigenvalues. We're going to use them. These omega, these are things that we're going to discuss tomorrow as well, have to do with the jump, the discontinuity that the solution would have across the interface. Remember, one thing we're trying to worry about is if we have a shock front that's propagating from right to left, we want to get the right quantity here, or vice versa. And if we have a rarefaction where the system is just depleting itself, we also need to react. So this will allow us to evaluate the fluxes, introduce a tiny bit of dissipation along the direction that we need. So now let me tell you what these things are. Okay, so here, what we're doing is, I'm going to expressing what is it, what I'm going to interpret the value of the function, and again, for the time being, think of this P as Qs. We're going to, tomorrow is going to be very clear what I introduce P's as opposed to Qs. For the moment, think of them as Qs. So what we would evaluate at the left, notice what we have. It's the value that we have at the cell I, plus something, this is going to be a slope, times the distance between the center of the cell I to the place where the interface is. So this is just this distance. So we're saying, take the value at the center and just do a Taylor approximation to first order to predict what's going to go to the right, to this side on the interface from the left side. R is the same thing, but now take the value at the cell plus 1, which is the one here, and interpolate to the left to define something on this right side. Of course, at the end of the day, we're going to add it up. If we have a solution that is perfectly smooth, this and that are going to be very close to each other. The error will be higher order, and there is no jump. So this one goes away, and these two just add up to what we would have done had we been dealing with a solution that is perfectly smooth. But there's another thing that is crucial that I have yet to tell you is what is the slope? So this slope is defined. Let me give you the definition first. So this is just the slope that you would evaluate knowing the value, say, the average value of this cell and the average value of that cell. However, that's not all there is to it. There's a crucial missing piece in here that I haven't told you what the mean mod is. So this is the standard slope that you have obtained at the left of the interface, or computing things using the left of the interface, or computing things using at the right of the interface. But now there is something else in this definition, and I'll tell you what this is. Okay, so this is where it really looks like black magic. But what you've done in here is that you're going to say, take the two slopes, the one you would obtain from that cell and the one you obtain from the left of that cell. Yeah. Because I'm in here. Because I'm proper to the left. Here, that's a positive value to the left, so I'm coming back. So in one case, I'm going from I to I plus a half. The other one, I go into I plus 1 to I plus a half. Right, so this one I'm centering here. And so I need to subtract a little bit to go to the I plus a half. And the other one is centering at I, and I'm going to the right. But this one is where I said it's doing a little bit of black magic. It's basically telling me if the two slopes happen to be of different signs. So if I have a function that is behaving like so, I said, well, just use zero slope. Because what this is saying, no, we are either dealing with spurious oscillation and we don't want to make them, to exacerbate them. And so they just make a first order approximation, that's all. Don't use any slope. And this one is take the smallest of the slope. Because remember, we're trying to minimize the spurious oscillation, so this will get it done. So if both are the same, but I have this one like so, they're both positive, well, take that one, which is the smallest one. So once you put all this together, there are several ingredients in here. So one is this one. It's just trying to react to both spurious oscillations and the fact that you might have very sharp gradients. So that's this one. This piece is recognizing that because at a shock interface, you can truly have a state from the left that is different from the state of the right. So you're going to average these two. And because of, again, some high frequency content that can be induced, you're going to add a little bit of this. These are jumps conditions we're going to discuss tomorrow. These jump conditions are the ones that are dictated to us by the problem and the fact that we want to pick that unique solution. Remember, there was a condition that we want to pick of all the possible weak solutions, the one that maximizes the change of entropy. That's part of the reason why that term is there. So if you go to the literature, in particular Levesque's book, you're going to find a whole slew of these solvers. There are lots. Those change depending on how much information you want to use of your full problem. There are some that actually don't use all the eigenvalues, but use the largest one, let's say. Some don't even use the eigenvalues. Some attempt to get a higher accuracy implementation. So there are many of those, but all of them have, one way or another, these ways to react to the particular pathologies that will be generically showing up in a case where we have something like that, where the speeds of propagation depend on the solutions themselves. So tomorrow or the next lecture, we're going to go slowly on how we apply these in not relativistic hydrodynamics, but in Newtonian hydrodynamics, just so that you have an example. No, actually, it's going to be relativistic hydrodynamic, but on a flat background. We're going to use that and explicitly go with that example because as you can take over. Some of you might have done this homework with Sasha, where you actually implemented wave equations. So if you have that code, you can just modify it a little bit, change the equation so that now you don't have a constant speed of propagation, but you have a speed of propagation that is given by the solution itself. See the problems you have to face with, and then you can implement this method in particular. Okay, we're going to stop here. Thank you. Any questions? No? Still not getting a lot of pushback from you guys. I imagine it has to do with, I hope it has to do with you guys being here for the third week and we just coming and then all energized. But again, pushback. That would be good. Thanks. So I think now there are goodies and then we'll start again with Daniel. Right.